Yeah, thank you for letting me talk here. So I'll be talking about an investigation into halo disk angular momentum correlation, and I'm based at UWA, and this is work I'm primarily doing with Daniela Bresco. So a little on why should we study the evolution of angular momentum. So as we just heard, angular momentum is a conserved quantity in a closed system. Therefore, the angular momentum of a galaxy has to come from what was there initially, or from extreme tidal torques. So I think a lot of people, we've just seen this plane, so I think a lot of people, when they think of angular momentum, think of it in this kind of specific angular momentum mass plane. So here I've got the specific angular momentum of a dark matter halo versus the halo mass of the halo mass. And when you think of the spin parameter in this plane, you can think of it as kind of the scatter off this relation. So from in a cold dark matter universe, you expect galaxies to sit along this this m to the 2/3 relation. So you can think of the spin, which is given in that equation there, as being kind of scatter off this relation. So it's a specific angular momentum over the, or proportion of the specific angular momentum over the mass of the 2/3. So a useful relationship to use in order to study the journey of angular momentum from a dark matter halo to the galaxy is therefore that between the spin of the galaxy and the spin of the dark matter halo. And so you can expect, if everything's conserved, you could expect this might be 1-to-1, for example. So what are simulations telling us so far? So here I've got an example from some cosmological zoom simulations. This is work by Jiang et al. 2019. And I've got a couple of things to point out. So here they've got on the y-axis the spin of the galaxy, and then on the x-axis the spin of the halo. And so how did they define a galaxy? So they used cold, dense gas and stars, and they also used a radial cutoff of 0.1 times the virial radius. So however, when I'm going to talk about galaxy spin, I'm actually going to use a slightly different definition of your galaxy. So I'm going to use a ISM, interstellar medium, that is circumgalactic medium conversion. I won't discuss now, just for time's sake, but and also the stars. And I also actually use a slightly different radial cutoff of the virial radius. The 3 parallel lines on here show the FJ parameters. So this is the spin of the galaxy versus over the spin of the dark matter halo. So you can see the dotted line there is 1, and then you've got the dot dash line is 0.2. And you can see a lot of the galaxies are definitely below that 1-to-1 line. And these crosses here are actually the 16th to 84th percentiles on each axis. And finally, in the bottom right, you can see the correlation coefficient, which is what we're really interested in for this work, how much these two correlate. So you can see from these zoom simulations that this is actually showing kind of negligible correlation, and even like slightly negative on the left there. And what I should also say is for each galaxy, different redshifts are shown here. So you've got one galaxy shown in multiple points. So it's clear from the zooms that there is this kind of negligible correlation between the two. But is this true when we apply this analysis to cosmological simulations such as Eagle and Lustrous, where you're not just looking at a selection of galaxies, you're looking at a whole kind of volume? So I've applied this analysis here. So on the left there, you're seeing exactly the same plot as we've seen before. So you've got those percentiles, you've got the 2 sigma ranges, the circle, and you've got those FJ lines there as well, and it's galaxy spin versus halo spin. And for this, we've used a criteria. So as we heard from Matt's talk, some of these galaxies will be subjected to numerical heating. So we're using kind of a resolution cut, 10 to the 8. So the masses we're using centrals and a redshift 0. We're just taking more than redshift 0 for this plot. And you actually see a positive correlation coefficient, this of plus 0.46. So still sort of slight, but it's there. So what about if we include different redshift as in the original plot? So this is where we've included redshift 0 to 4. And you still see this positive correlation, even when you include the different redshifts at Eagle. So is this positive correlation true for different cosmological simulations? It's a fair question to ask. So here we're actually putting on illustrious TNG50 galaxies as well. These have got a slightly different, so the Eagle galaxies, we heard from Rubies and Hesselanden, I'm using the who introduced Eagle. I'm using the recalibrated 25 megaparsec box, and so the illustrious uses a 50 megaparsec box, or the simulation I'm using does. So I use a slightly different stellar mass cut, but I'm showing the results here in red, and so you're seeing slightly different values. You're seeing it kind of closer to FJ, between FJ 0.5 to 1, but you are seeing this kind of positive correlation, and that's really what we're interested in for this talk. So this does beg the question, where are these differences coming from? Why are we seeing a difference from the Zoom simulations compared with the cosmological simulations? And can simulations reach consensus? So to answer this question, we need to understand the journey of angular momentum from the halo to the galaxy. And a natural place to start looking is the circumgalactic medium, or CGM. So if we split, we use that interstellar medium, circumgalactic medium split that I talked about earlier. And applied this to the Eagle galaxies. This is the redshift 0 Eagle galaxies. We get this. So orange is the circumgalactic medium, and purple is just the galaxy. And it's clear that there is a disparity there. You're getting higher circumgalactic medium spins and yeah, lower galaxy spins. So it's clear that the journey of angular momentum from halo to galaxy is not completely linear. It's not one-to-one. So we don't know if the circumgalactic medium has been impacted by the galaxy itself or by large-scale processes. And so the great thing about simulations is we can use them to remove the galaxy evolution physics entirely and concentrate solely on the circumgalactic medium dark matter interplay. So this is what we've done here. So a good place to start was we went to the Genesis Hydro simulations run by Chris Power. So these are two boxes. Well, multiple boxes, but this a small box does 12 megaparsec over H. And when I say, and they're non-radiative simulations, when I say that, I mean they don't include radiative cooling, star formation, stellar feedback. And actually, Chris has actually run these with multiple different codes, and I've got two examples here, the AMR code repo and Gadget 3 on the right. So they're different hydrodynamic schemes there. And you can see the structures, as you'd expect, largely follow one another. So I've got temperature plot there, projection slice. But what about on spin plane? So here we have the halo gas dark matter spin plane. Instead, it's just that taking the total gas associated with that halo within the aperture of that virial radius. And the main thing I wanted to point out here is that when you look at that FJ value, it's around 1.43 for Gadget 3 and 1.79 for Arepo. And they're different within themselves, which is quite interesting anyway. And we need to kind of explore that a bit further. But when we compare this with something like Eagle, you can see the FJ value is 3.6. So it's fairly a lot higher when you include kind of that galaxy evolution physics. So these results suggest that galaxy evolution physics is playing a role here. So this time, we can use simulations again to separate the internal galaxy evolution physical processes and how they impact both the spin of the galaxy and the circumgalactic medium. So to do this, I've run a set of idealized or control simulations. So these were run with Gadget 3. They were run for 4 gigayears. They started off with a dark matter halo and a gaseous halo sitting inside it, same density profile. And what I did, I just turned on cooling, I turned on star formation processes, star formation, and I turned on stellar feedback. So I've got a movie here that shows all of these, and the gas is in red, the dark matter in blue, and the stars in white. And as you see, the movie starts once the star formation's kind of started. So here's an example here. So you can see that stellar feedback's pushed some of that gas out, and you've got this kind of spin. Apologies for the poor time resolution, hence why the you can see that kind of stellar structure of the bar moving at different kind of jerky ways. That's why. Okay, so what I've done with these simulations is I've used I can use the simulation to explore lots of different things. So I can use, for example, different stellar feedback mechanisms. I can turn off stellar feedback. I can use different initial spins, and I can use do a whole parameter study and check which galaxy evolutionary processes are affecting that relationship. So I've got some examples here. So these are some of the runs that have run to completion. Some of them are still going. We've got quite a few. And to show the power of these runs, I'm just going to pick these two to show you. So these are two. One includes feedback and one includes no stellar feedback. And they are run with the same initial conditions, a Milky Way-sized galaxy. Initially, you can definitely see that the gas has moved further when you've got stellar feedback. Obviously, it's been ejected, and you can actually see different stellar structures. It's quite interesting. But when I plot this on this plane, and I actually plot the tracks of these galaxies on this plane, it becomes quite interesting. So this is the if we focus on the left there, this is the spin of the galaxy versus the halo. And you can see for the stellar feedback case, this is above that of the no feedback case. So the FJ value is above it. And on the right, we've got the circumgalactic medium spin, and we've got the no feedback case is actually above it this time. So we've got kind of the reverse is true. So what's happening here? So the gas is cooling at the center of the halo first, where the angular momentum is lower. And the stellar feedback is able to eject this lower angular momentum gas into the circumgalactic medium, lowering the spin of the circumgalactic medium compared with the run that does not include feedback. And this is interesting. This difference is actually exacerbated by the inclusion of a hierarchical assembly history. And actually, if anyone's heard of the angular momentum catastrophe, this is kind of one of the driving forces behind that when you don't include feedback. So this is just an example of the power of one of these control simulations. So to summarize, hopefully I've convinced you that the journey of angular momentum from the large-scale dark matter halo to the galaxy at its center is more complicated than simple angular momentum preservation, even for the simplest isolated galaxies. There are still many questions to be answered. And simulations offer an excellent way to study this journey, and we can use them to focus on different stages. Well, thanks.